I'll be talking about the control, which is the major part of this circuit. It does controls the whole circuit. It tells each of them when to pop, when to push, when to remove that, where to pop or where to push from. So let's go in. It's almost big, but I'll just briefly talk about certain parts of it. I won't go deep into all of them. I won't go deep into the whole part of the control. So first of all, you have here. Let me complete it. It's supposed to be, but the output was not needed. But I'll just show you what it's like. So this part is the counter. This part is a counter. It's just a continuous counter that keeps tracks of how many pops or push that have been done. So usually you can decide to push twice. So this is the counter that checks whether you've used the push to button twice. You can choose to pop 4 times and so on. So you can see that it has the, so this multiplexer sets it to 0, another one sets it to 1, else it's incrementing. So this is the counter here. This is a counter register that does the job of counting for the whole control circuit. So when you go to the Velo code, you will see it on my website. You will be able to map and trace how this particular counter works. So, but I won't start going deep much there. A lot of explanation is on the code itself. So again, is this deselect. So this deselect, remember when we were talking about the data part, we talked about the multiplexer, those 4 inputs multiplexer we met when we were talking about the data part. This is where the control comes from. You choose which of them to select. You can see them here: 2 3 0 0 0 0 1 3 0. So usually with the help of the counter, this is where the counter comes to. So it checks for whichever value the counter is, which deselect do you want. So whenever it's 0 0, it means it's selecting from our normal data input. If it's 1, it's selecting from the LU output. Then if it's 2 and 3, it's selecting from the B register with one delay and just the B stack. Sorry. So this is where the deselect is being generated from. I threw more light on it when I was discussing the data part. So this is the select for that multiplexer. Then again, this is where the push signal is being generated from. So there are 4 different conditions for the push. So this is condition 1, condition 2, condition 3, condition 4. So if any of them is on, this is the OR gate that checks if any of them on. Then the signal, the push signal comes here. So therefore, I don't think it be necessary. So, but when you go through the code, I named them push 0, push 1, push 2, and push 3. So they represent these 4 conditions. This flip-flop stores the 4 of them. So depending on whenever they are on. So then again, now whenever the push is on, you still have to determine which of the push, whether it's push A or push B. So that decision is where it's made. So first of all, the normal push, so whenever the push comes on, it comes here, goes into these 2 AND gates. Now this is your A in, the data that is going into the stack. So whenever it comes here, it checks the MSB, whether it's 1 or 0. If it's 1, it goes to push B, which indicates there is an operator. If your MSB is 0, it goes to push A, which indicates that is a figure. Then the pop B is also generated. So pop B comes immediately after push. You pop. I won't explain that here. It should be explained when you read the code. Pop A. Then this is your LUA and LUB. This is where the signal that turns the 2 LU registers on, LUA and LUB. So first of all, the LUB first of all comes on. Then after one delay, using this D flip-flop, LUA comes on. So B comes on first before A, but it's still the same condition and signal that turns them on. So this is used to shut down the calculation. When stack B, this is the stack pointer, is less than 1, that is when it's in 0, stack A is equal to 1, and in position, this in position is from our ACC in, the position of the stack in our ACC in. So if it's 0, so these three conditions means when the three stacks are empty, B and A are for the two stacks for our operator and our logic. And reason why A is equal to 1 is because A will store the your final output. So it won't be at 0, it will be at 1 to still contain the final output. So this in position stores the, remember it's coming from the ACC in, is the stack pointer for our inputs. So whenever it's at 0, it means everything is over. There's no more data to be operated on. So when these three conditions are on, that is when our is empty. Where is it? Okay, I named it done here, but on the top of the circuit I renamed it as is empty, because that's what I used to explain it on the code on my website. The signal is referred as it is empty. Now this is where that gray signal comes in. It compares the two operators and checks which one is greater. So depending on the output, the signal comes here and influences whether to pop or to push. So that is my little explanation for the control circuit. So at this point, I think I've explained each of these subsections. Then in our next tutorial, I'll run a particular example so we see how this core works. So thank you. Subscribe, like, and share this video. Thank you.